Okay, so we've done the one sample P. Now let's look at the two sample P. What do I mean by that? I mean that let's say we've got two populations. We've got population 1, we've got population 2, and the prevalence in population 1 is P1, and the prevalence in population 2 is P2, and we're going to take a sample from population 1 and a sample from population 2, and we will get the sample versions of our estimators of P1 and P2 and then compare them. Now, just as in the continuous case, we want to compare P1 versus P2. And the primary hypothesis of interest is going to be when P1 is equal to P2. So is P1 equal to P2? All right? Well, there's two ways of determining this. One is to look at their differences. So look at P1 minus P2 and ask, is that equal to 0? And that is exactly what we did with the two mean situation in the continuous case. And I'm not going to look at this. I'm going to leave that up to you to determine. The data programs are all there and everything. Another way of determining this is to look at the ratio. Look at the ratio P1 over P2 and ask, is that equal to 1? And this is very interesting. You just have to be careful when P2 is equal to 0. You don't want to be dividing by 0. Okay, but this is one way of doing it. Another way of looking at the ratio is our old friend's odds. So this hypothesis that the two are equal is equally validly tested by looking at the odds. Look at the relative odds under P1 and under P2, or the odds ratio, if you want to call it that, and ask, is that equal to 1? That should be a 1. So this way of testing the hypothesis, this way of testing, this way. So this is relative risks. So this is relative risks. And this is relative odds, or odds ratio, if you will. This is the one that we're going to be concentrating on. This one has very much nicer statistical properties than this, so let's look at this. Clearly, the two are either both equal to 1 or they're not, and simultaneously. So why not go with relative odds? Okay, let's have a quick refresher about relative odds. And remember, if the probability of an event is A is P, I'm just recalling what we saw in the past, then the odds of the event are P over 1 minus P. Sometimes you see this stated as P to 1 minus P, the ratio of P to 1 minus P. Now, you also see this in the literature quite a bit, that if P is tiny, then the odds are approximately the same as P. And that's because if you're going to expand 1 minus P, 1 over 1 minus P, that's the same as 1 plus P. And so this is approximately equal to P because you'll leave out the P squared. So if P is tiny, then if P is approximately 0, then this quantity is going to be approximately equal to P. So the odds, when P is small, the odds are equal to the probability of the event. You'll see that in the literature. You can actually see what that means. What we've plotted here is the difference between the odds of an event minus the probability of the event when the probability is less than 0.1. And you can see that the difference is, well, it gets to be sizable up here, of course. Although, you know, it's not that much. It's 0.01 or so. But down here, you can see the difference is tiny. So anyway, there's a graphical representation of that statement. And just to remind you, if the probability is 0, the odds are 0. If the probability is 1, the odds are infinite. Up to a half, excluding a half, but below a half, the odds are going to be less than 1. And they're equal to 1 at a half. above a half, the odds are going to be bigger than 1. Okay, so that's how you relate odds to probabilities. Remember, sort of half is in the middle, you know. Less than a half, then the probability of an event happening is less than the probability of the event not happening. And what that translates to in odds terms is that the odds are less than 1 when the probability is less than a half. And the odds are equal to 1 when the probability is a half. And then it's bigger than 1 when the probability is bigger than a half. Sometimes you see odds as stated in this way. So the odds of a third are sometimes stated as 1 to 3. Odds of a half are 1 to 2. Evens 1 to 1. When you get above 1, then it's 2 to 1, 3 to 1. Instead of 2, it's 2 to 1, 3 to 1, etc. So this just depends on the culture you're in, etc. But once you know the odds, you know the probability. Once you know the probability, you know the odds, however you're going to express the odds. Okay, now here is the real strength of the odds. The real strength of the odds is when you look at the odds ratio or relative odds. And this is what happens. Now I'm going to recall the Bayes theorem. So if you want to go back to Bayes theorem and take a look at Bayes theorem and remind yourself of what it is. But here we go again. Suppose we have a disease such as lung cancer, and we've got two groups, smokers, non-smokers. Now, what are the relative odds of the disease? So the relative odds of the disease for smokers versus non-smokers. So for smokers, here is the probability of getting the disease, or the odds rather, of getting the disease. It's the probability of getting the disease for the smokers, remember we're always talking about the smokers, over 1 minus. So the odds, remember, was P over 1 minus P. So here it is, here's the P, and there's the 1 minus the P, and this is for the smokers. For the non-smokers, this is for the non-smokers, it's the P over 1 minus P again. And it's relative odds, or odds ratio. So you divide the one by the other. There's the division. So that's the relative odds of the disease for smokers relative to non-smokers. Now, from Bayes' theorem, the probability of the disease for smokers, given that you're talking about smokers, is, now remember, we could flip it around. It's the probability of the disease times the probability of being a smoker, given that you've got the disease. You're flipping it around. Here you want the disease giving the smoker. Here you're going to flip it around. Smoking giving disease. And then you put that same thing down here, and then you do it for non-diseased people. So probability of not having the disease and the probability of being a smoker, given that you don't have the disease. So the odds, if this is the probability, the odds are the probability divided by 1 minus probability. Things cancel out so that you're left with this rather nice situation here. Now, the probability of the disease times the probability of being a smoker, given that you have the disease, divided by the probability of not having the disease, times the probability of smoking, given that you don't have the disease. So, the odds ratio. Now, look at the odds ratio. That means we have to look at the probability, the odds of the disease, that's this one, given that you're a smoker, and then the same thing when you're a non-smoker. So just go back here and replace the S by SC, and that's what you get here. And so that's what you get, okay, after a tiny, tiny little bit of algebra. And now the fun thing is to just rearrange these terms. So if you just rearrange the terms, you'll come with this, and now just swap these two, which is perfectly legal. Just swap those two, and you've got this. And now what is this? This is the probability of being a smoker, not being a smoker, given that you have the disease. Well, that's 1 minus the probability of being a smoker. What is this one? It's the probability of not being a smoker, given that you don't have the disease. Well, that's just 1 minus the probability of being a smoker if you don't have the disease. So then, look at this. What is this? This is our old friend p over 1 minus p. This too is a p over 1 minus p. So this is the ratio, so this is the odds ratio of what? It's the odds ratio of being a smoker given that you have the disease over the odds ratio of being a smoker if you don't have the disease. So this is the odds ratio of being a smoker for diseased versus non-diseased. We're sticking with the probability of being a smoker. It's the odds of being a smoker. So what we've done is we've gone from the odds of disease, smokers to non-smokers, to the odds of smoking given disease and non-diseased. So if you're interested in this quantity, if you're interested in seeing whether the probability or the odds of the disease of smokers to non-smokers, then that's exactly the same as the odds of smoking amongst diseased people and the odds of smoking amongst non-diseased people. So you can go from this. How would you find the probability of having disease given that you smoke? That means you would have to follow people through the lifetime and see what is the probability that smokers get the disease, namely lung cancer, and following the non-smokers through the lifetime and seeing which ones of those get lung cancer. And we flip things around, so now we're talking about the probability of smoking given diseased people. So now find me a group of people who do have lung cancer, and let me see what proportion of them smoke. Find me a comparable group who don't have lung cancer, and let me see what proportion of those smoke, and the two are identical. That's the whole theory behind a case control study. So you've seen this before. I'm just reminding you why this is so. It's Bayes' theorem that makes it so.